Let us talk about a few basics of game theory. So I'll just start with an example. Let us say there are two players in a game. So there is a game in which the players have strategies, and we need to define the number of players, their strategies, and what are the payoffs of each of these players whenever they're going to take some actions. So let us say there is a player A and there is a player B. Player B has two choices, left, right, and player A has two choices, top, bottom, right? And these are the payoffs. So every time the first number here shows the payoff of player A, and the second number here shows the payoff of player 2, right? So if player A plays top and player B plays left, the payoff to player A is 1 and the payoff to player B is 2, right? 0 1 2 1 1 0 2 1 1 0, right? So this is what the payoff matrix it looks like. Hmm. Hmm. Now just think about it. Player A, I'm player A and you guys are player B. So I have a choice either top or to play top or bottom. You have a choice either to play left or right. The first number every time is showing me my payoff, and the second number every time is showing your payoff, right? So if I play bottom, hmm, now just think about it. This 2 is greater than 1. This 1 is greater than 0. So whether you play left or you play right, the payoff I'm going to get from playing bottom is more than the payoff I'm going to get from playing top, right? So for player A, bottom is the dominant strategy, right? Okay, it is a dominant strategy. So whatever, whichever choice, please write, whichever choice B makes, A always chooses bottom. A always chooses bottom. Now think about B. Think about B. These second numbers are for player B. Just think about it. Your and he has a choice between left and right. 2 is greater than 1. 1 is greater than 0. Hmm? So whatever, whether player A plays top or player A plays bottom, player B is better off playing left. Hmm? Whether player A plays top or player A plays bottom, player B is better off playing left. So what do you write? Whichever choice. B always chooses left. B always chooses left, right? So it means what? It means that there is a dominant strategy. For player A, bottom is the dominant strategy. For player B, left is the dominant strategy, right? So there is a dominant strategy. Whatever the other player plays, if I have a dominant strategy, I'll play only that strategy. That is what dominant strategy is. So whatever other player plays, it doesn't matter. If I have a dominant strategy, I will be playing my dominant strategy only, right? So there is one optimal choice of strategy. Please write. There is one optimal choice of strategy, right? For each player, no matter what other player does. No matter what other player does, right? So this is what the dominant strategy is. Whatever whatever be your strategy, it doesn't matter. If I have a dominant strategy, I'll be playing my strategy only. That is it. I'm not even concerned with what you are playing. So if there is a dominant strategy for each player, you can actually predict that that is going to be the outcome of the game. Hmm. So here in this case, bottom is a dominant strategy for player A, left is a dominant strategy for player B. You can easily predict that bottom left is the equilibrium outcome of this game, right? So if there is a dominant strategy, please write. If there is a dominant strategy for each player in the game, right, then we would predict that it would be the equilibrium outcome of the game. That it would be the equilibrium outcome of the game. So you have here in this case, bottom left is the equilibrium outcome. So bottom is the equilibrium strategy for player A, left is the equilibrium strategy for player B, and we'll be playing this with a payoff 2-1. With a payoff 2-1, right? Okay, so equilibrium outcome is this bottom left, 2-1 here. Okay, so here this was the case where dominant strategy equilibrium exists. So you can just write somewhere here. Dominant strategy equilibrium exists. Hmm. Dominant strategy equilibrium exists. So uh, this is what the case for the dominant strategy equilibrium. Now let us look at the case where the dominant strategy does not exist. So let us look at the case when dominant strategy equilibrium does not exist. Mhm. Dominant strategy equilibrium does not exist. So let us just change the payoffs a little bit for the same game. So there is a player A and there's a player B. Player B plays left, player B plays right, player A can play top, player A can take bottom, can play bottom. And these are the payoffs. Now 2-1, 0-0, 0-0, 1-2. Hmm? 2-1, 0-0, 0-0, 1-2. Now just think about it. Whether is there a dominant strategy? Hmm. Is there a dominant strategy? Just think about it. For player A, in case if it plays only top, so 2 is better than 0. Yes, definitely, but 0 is not better than 1. So he will not play top. Top is not the dominant strategy, and similarly, not even bottom. So 0 is not better than 2. It's gone. So you don't have to worry about it. 1 is although better than 0, but fair enough. So bottom is also. So there is no dominant strategy for player A. Similarly, for player B, 1 is better than 0, yes, but 0 is not better than 2. So left is definitely not a dominant strategy for player B. Similarly, 0 is better than 1. Oh, sorry, 0 is not better than 1, but 2 is better than 0. But since 0 is not better than 1, right is also not the dominant strategy for player B. Right? So there is no dominant strategy exist. So instead of requiring a very strict rule that whatever other player does, I will play my dominant strategy. Instead of requiring that, I can require something else. I can require something else that we are going to find out the optimal for the optimal choices of B. So A is going to find out optimal for the optimal choice of B. B is going to find out optimal for the optimal choice of A, right? So if A's choice is optimal for B's choice and B's choice is optimal for A's choice, that is what Nash equilibrium is. That is what Nash equilibrium is, right? So please write few points. First thing you know, here dominant strategy. Here dominant strategy equilibrium does not exist. First thing. Second thing, rather than A's choice be optimal for all choices of B, we can put a weaker condition that A's choice be optimal for the optimal choice of B, right? So rather than A's choice be optimal for all choices of B. What do I mean by this? I mean by this that you have a dominant strategy equilibrium in the earlier game. So A was playing bottom whether B was playing left or right. B was playing left whether A was playing top or bottom, right? So rather than requiring that, what we can do is this. We can just require we can just require that it would be optimal for optimal choices of P, right? From for optimal choice of P, right? So, but whatever B's choice is going to be, it depends on what A is also doing. So, what is meant by a Nash equilibrium then? So it is a pair of strategies if A's choice is optimal given B's choices and B's choice is optimal given A's choices, right? So I'll define that, but let me just tell you how do you find that out. So if player A plays stop, hmm, what is the best for player B between left and right? He will be comparing 1 and 0. Comparing 1. So I'll put a sign here. Now player B plays left. Player A has to compare between top and bottom. So he's comparing 2 and 0. What will he do? 2, right? So you have two underscore signs here. This becomes a Nash equilibrium. Similarly, if player A plays bottom, player B has a choice between left and right. So he's comparing 0 and 2. What is going to do? He's going to choose 2. That is right. If player B plays right, player A has a choice between top and bottom, right? So he's comparing 0 and 1. What will you do? 1. So you have a Nash equilibrium here, right? So there are two Nash equilibriums. There are two Nash equilibriums. So let me just define this. Let me just define this. A pair of strategies. Where should I write this? A pair of strategies is a Nash equilibrium if A's choice is optimal for B's choice and B's choice is optimal for A's choice, right? So neither person knows what other person is going to do when he is going to make a choice, right? His choice of the strategy, right? So we have a Nash equilibrium if each person is making the optimal choice given the other person's choice, right? So let me just do this once more. Player A plays top. Player B has a choice between left and right. He's going to choose between 1 and 0. Let's say he's chosen 1. So I have underlined this one. What's let's say? I mean, he will be choosing 1 because he's getting a higher payoff from playing left. When player B plays left, player A has a choice between top and bottom. So he's comparing 2 and 0. He's going to choose 2. So this, I'm going to mark this. So you have the two underscores at the same time. So what is A doing? I mean, A is making the optimal choice given the other person's choice. Given the other person's choice. So if, what do you mean? Given the other person's choice means given player B is going to play left, player A is better off playing top. Given player A is playing top, player B is better off playing left. That is what this means given other person's choice. Similarly, if player A plays bottom, then player B is going to make a choice between left and right. So he's comparing the pair of 0 and 2. He's going to take up 2. If player B is going to play right, uh, player A has a choice between top and left. So he's comparing 0 and 1. He's going to choose 1, right? So you have the Nash equilibrium out here. So there are two Nash equilibriums out here. Uh, there are two Nash equilibriums out here. Okay, so we'll take the discussion further tomorrow. Thank you, beta.